This video will cover transformations, and we're specifically going to look at an XY coordinate, because if we can understand how to move a single point, let's call this A, if we know how to move this around, whether it be sliding it, dilating it, reflecting it, or rotating it, those are the four situations we'll look at, then if we have a figure, which would be multiple points pieced together, we can just apply the transformation to all those points, and the figure will behave exactly as we want it to. So if we understand a single point, that conceptual idea, we just apply that to multiple points, and that will move the figure the way we would like. Before we start with the actual transformation types, let's just understand what piece of the XY coordinate controls what type of movement. So the X coordinate, because the axis runs horizontally, the X coordinate will control horizontal movement. The Y coordinate will control vertical movement, since that Y axis runs vertically. Understanding that idea, you've already won half the battle with transformations. Okay, so now let's go into each type. The first is a translation. A translation is just a slide. Okay, the operation that's going to be used is addition, subtraction. So let's look at the four scenarios that we could have. We could move it right. Let me move this over slightly. We could move this right. We could slide a point left. We could move a point up, or we could move a point down. Okay, and we can chain these together if we would like as well. So let's look at each one individually. If we have a point XY for each one, and we want to apply each individual transformation to that point. For moving something right, what we're going to do is add a value to what coordinate? Well, right is a horizontal movement, so you can predict that the application of this operation will be to the X coordinate. So what we're going to do, we want to move right, which on the coordinate plane is in the positive direction on our x-axis. So we add a value to the x, whatever the desired amount of space we're trying to move is. We don't have to alter the y coordinate, because again, we're only moving horizontally. So because there's no vertical movement, there's no application to the y. Now, I have some number k there. Let's define what k is. We're going to call k some positive real number. Now left. Moving left will be in the negative direction along the x-axis. So if I want to move that way, we're going to subtract some number k. To move it up, now I'm going in a vertical direction. Going up is in the positive direction on my y-axis. So this time I'm going to alter the y coordinate by adding some value to y. And down, we're moving in the negative direction along the y-axis, so we subtract. So we'll just take one more note off to the side. These first two, those are horizontal, and therefore that is controlling the x coordinate, right? The last two are vertical movements, which is why we're only altering the y coordinate. And before we move on, when we decide to apply our points, let's say I'm starting at some point A, some XY coordinate. Once I move that, we define it with some new notation. You'll put a little apostrophe up at the top. So this first piece, before the transformation is applied, this is what's called the pre-image. Okay, so the pre-image are the points prior to the transformation. Once you've applied the transformation, that is called the image. Okay, so you're going to see those vocab terms in various problems. And again, we don't have to just apply one transformation. We could chain transformations together. So I could shift it left and then shift it down. My new point, I just add a tick mark. So it would become A double prime. I could shift it back to the right, and we could call it A triple prime. Okay. So by adding those little apostrophes or those little tick marks, you're showing the order in which the transformations are applied on the coordinate plane. You could see that I go to A prime first, then A double prime, then A triple prime. And again, pre-image, prior to transformations, image, after transformations. So that is a translation. Now, reflection. When we make a reflection, what we are doing is we are moving a point to a mirrored position across some designated line. That designated line, it's called the line of reflection. No surprise there. But what we should see is once we've done that, the points, so the image and the pre-image, should be equidistant from the line of reflection. Now we're going to look at, so I'll even star this, what operation is going to be used for reflections. The operation we will discover is multiplying by specifically -1. So we're going to look at 3 scenarios. We want to reflect over the x-axis, over the y-axis, and over the line y equals x. Okay, so why is it multiplying by -1? Let's say we have a point 1, 2, and I want to flip it over the x-axis. So the x-axis in this case is my line of reflection. I move it to a mirrored position. It would be at 1, -2. And you can see that these points are equidistant from the line of reflection being both 2 units away. So if we take the point 1, 2, to get a proper mirrored position that is equidistant, I would have to put it at 1, -2, and you can see we're just multiplying the y coordinate in that case by -1. So why is it multiplying the y coordinate to flip over the x-axis? Well, let's take note off to the side. Over the x-axis, that is a vertical movement. And a vertical movement is going to impact the y coordinate. Over the y-axis is a horizontal movement, and that's going to impact the x coordinate. So let's take a look at the actual abstract notation. So if we have a point xy, what must we do to showcase the reflection? Again, in the first case, vertical movement, so I'm altering the y coordinate. So in this one, we're just going to multiply just the y coordinate by -1. For over the y-axis, that is a horizontal movement, so we're just going to multiply the x coordinate by -1. Okay, and again, if we look at our coordinate plane, if I have a point, again, if I'm going over the x-axis, you can see we have vertical movement there. If I'm going over the y-axis, we can see we have horizontal movement. So think about the movement in this case, not the actual letter of the axis. So the last one is how do we flip over the line y equals x? So I'm going to draw the line y equals x. Hopefully from Algebra 1 you remember how to graph a linear function. So the line y equals x. This has, remember, our standard format for linear function. We can see that the slope in this case is 1. And b is equal to 0. So it has a y-intercept of 0 and a slope of 1. So it will look something like this. If we have a point that we're trying to reflect over that line, so that it is equidistant, the way you do that is swap the x and y coordinates. So if you have some coordinate x, y, you switch it to be y, x. And that is how you reflect over the line y equals x. Now, onto a rotation. So for a rotation, we're going to move a point some amount of degrees around a point or around a designated point. There's not really an operation for this, so I'm going to give you some shortcuts on how to derive these formulas. If you forget them, these are the ones people most often forget. So we're concerned with 3 types of rotation. We're going to do 90 degrees clockwise, around the origin. We're going to do 90 degrees counterclockwise around origin. And then we are going to do 180 degrees around the origin. So recall a full turn is 360 degrees. So when we make these 90-degree turns, think we're going a quarter turn. For 180 degrees, we're going a half turn. So just keep that in mind. Now, to determine what we need to do for each of these, we'll just actually take our piece of paper and rotate it the desired amount of degrees, and you'll see what the resulting point should be. So if we take some point x, y for each, so let's say I have my piece of paper. We have a coordinate plane on it, and I plot some point at, say, 2, 1. What we can do if we want to discover where this point, or what the resulting point would be when I make a 90-degree rotation clockwise, what we're going to do is actually rotate our paper 90 degrees clockwise. And you'll see something like this. Okay, so if you actually want to try this, take a piece of paper, plot the point 2, 1. Don't make the x and y coordinates the same because you won't see what happens. So we went from, our original point was 2, 1. Now after the 90 degrees clockwise rotation, I am now at the point 1, negative 2. So I can see that this is an x, y coordinate. So what happened? It looks like the x and y switched, so it became y, but the x became negative. And that is the rule. When I have x, y, to rotate it 90 degrees counterclockwise, switch the coordinates, make x negative. Now, if we want to go counterclockwise, we can take our paper, start with the same point, we'll work with 2, 1. Now we're going to rotate 90 degrees counterclockwise. And we're at the point -1, 2. So what happened? We had an x, y coordinate. Now again, the x and y switched, but the y was made negative this time instead. So it's -yx. And then lastly, if we want to rotate 180 degrees, we can plot our point on a piece of paper. Again, we're dealing with 2, 1. 180 degrees would be a full half turn. So my paper will be flipped upside down. And we'll be at -2, -1. So what happened here? We had an x, y coordinate, and it looks like the x and y values are the same. However, they were both made negative. So let's go back to our rule. The result will be -x, -y. Now notice the x and y got multiplied by -1, so we can make the observation that a 180-degree rotation is the same thing as 2 reflections. We can go over the x-axis and over the y-axis. The order in which you apply these 2 reflections doesn't matter, so order doesn't matter. But this is a key observation that 2 reflections will result in a 180-degree rotation, as long as they're reflecting over the x and over the y. So again, if you don't remember how to do these rotations, you can actually plot a point, the point that you're given on a piece of paper, and physically rotate the piece of paper and write down what the resulting coordinate is when you look at that new coordinate point. It's that simple. Now lastly, we'll look at the dilation. A dilation is taking the point and expanding or contracting from or to the origin by some scale factor. Now the operation that we'll be dealing with dilations, we're going to be multiplying by something that's not -1, okay? It's actually, we're going to be multiplying by a positive number. So by some number, if you end up multiplying by some number that's less than 0, that isn't -1, then you can signify or identify that 2 transformations have occurred. You have a dilation because the number is not 1, but also because it's negative, there's a reflection there. So with dilations, we're looking at 2 possibilities. We're going to expand or contract. Another thought, or another term that's used for each one. For expand, you might see stretch, so interchangeable terms here, or compress or contract. So I may be using any of those 4 terms. So for an expansion, if we have a point x, y, to expand it away from that origin by some desired amount, we just multiply both coordinates by that scale factor. But to get an expansion, we have to make sure that k is greater than 1. Now, for the contraction Again, we multiply both coordinates by whatever the contraction value is. But to get a contraction, we can't just multiply by anything. That k value has to be between 0 and 1. So again, what are we going to look at here visually, just so you can get an idea? We might have some point, and if we scale it, if we want to expand it away from, so this is at 0.21. So say we want to do an expansion or a stretch by 2. The new point, we multiply both points by 2. We're now at 4,2. To give you an idea of what happened, it is now twice the distance away from the origin. That is what happens with the expansion. So the original point was this far away, and now, after the expansion, when we multiplied both coordinates by 2, this new distance is 2 times as far. Okay, so when you expand, you're multiplying your distance away from the origin by that scale factor. And likewise, if we made a contraction or a compression, we would be that much closer to the origin. So if I multiply by 1/2, I would be half the way towards the origin. Okay? So that is a dilation. Dilation, just multiply both coordinates. So let's highlight that before we end the video. So for both of these, both coordinates are multiplied by the scale factor. Okay, so make sure we don't just apply the scale to just the x or just the y. For now, or in this class, we're going to apply our expansion and contraction to both x and y coordinates.